Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the prompt. Begin. Edmund Halley's Synopsis Astronomia Cometicae, published in 1705, represents a watershed moment in the understanding of comets. This work, a culmination of years of meticulous observation and calculation, dared to propose that comets were not simply unpredictable atmospheric phenomena or ominous celestial portents, but rather objects moving along predictable, elliptical orbits around the Sun. This essay undertakes a comprehensive evaluation of the synopsis, meticulously examining its constituent sections and appraising the validity of its central claims through rigorous analysis. The ensuing exploration will navigate the complexities of Halley's reasoning, consider the historical context that shaped his conclusions, and assess the lasting impact of this groundbreaking contribution to astronomy. Section 1: Introduction and Halley's initial assertions. The Synopsis Astronomia Cometicae begins with a concise introduction outlining the prevailing confusion surrounding comets. Halley directly challenges the Aristotelian view of comets as atmospheric exhalations, a perspective that had persisted for centuries. He asserts vehemently that comets are celestial bodies traversing vast distances, exhibiting variations in apparent size and brightness due to their proximity to both the Sun and the Earth. Halley contends that these variations, previously attributed to the capricious nature of the heavens, are instead consequences of perspective and orbital mechanics. This initial section lays the groundwork for a fundamentally Copernican understanding of comets, positioning them within the solar system governed by physical laws. His implicit deference to Newton's recently published Principia Mathematica is evident, hinting at the gravitational framework that will underpin his subsequent analysis. The audaciousness of this opening declaration, in the face of entrenched astronomical dogma, cannot be overstated. Halley isn't merely proposing an alternate interpretation, he is setting the stage for a complete paradigm shift. Section 2: Historical comet observations and data compilation. Halley then embarks on a detailed historical survey of comet observations, meticulously compiling data from various sources spanning several centuries. The section is not merely a chronicle of past sightings, it demonstrates Halley's commitment to empirical evidence. He catalogues the comet's observed positions, brightness, and the timings of their perihelion passages, acknowledging the inherent uncertainties and limitations of pretelescopic observations. A crucial aspect of this compilation is Halley's discerning eye. He critically evaluates the reliability of different sources, recognizing the potential for observational error and subjective bias. He accords greater weight to observations made by experienced astronomers using calibrated instruments, revealing his understanding of measurement accuracy. By assembling such a comprehensive dataset, Halley provides a solid foundation for his subsequent orbital calculations. He acknowledges gaps in the data, notably for comets observed before the advent of systematic astronomical recording, but argues that the available information is sufficient to discern patterns and identify potential periodicities. Section 3: The application of Newtonian principles to comet orbits. The core of Halley's argument resides in his application of Newtonian gravitation to the motion of comets. He posits that comets, like planets, are subject to the Sun's gravitational pull and therefore move along conic sections, namely ellipses, parabolas, or hyperbolas. Halley explicitly states that while elliptical orbits would imply periodicity and return, parabolic orbits would suggest one-time visitors from the outer reaches of the solar system. He meticulously explains the mathematical principles underlying the determination of orbital parameters from a limited number of observations. He outlines the iterative process required to refine orbital estimates, acknowledging the complexities introduced by planetary perturbations, particularly from Jupiter and Saturn. Halley's painstaking calculations represent a significant advance in celestial mechanics. He does not merely accept Newton's laws as abstract principles, he demonstrates their applicability to a previously enigmatic class of celestial objects. He also clearly acknowledges the computational limitations of his time, expressing the need for further refinements as improved observations become available. Section 4 Analysis of the comets of 2007 and 2008. This section showcases Halley's most impactful claim, the identification of the comets observed in 530 by Apianus, was in 607 by Kepler, and in 682 by himself as a single object returning periodically. He meticulously compares the orbital elements of these three comets, noting the remarkable similarities in their perihelion distances, orbital inclinations, and directions of motion. Halley accounts for the slight variations in observed times of perihelion passage by invoking the gravitational influence of Jupiter and Saturn, recognizing that these planetary perturbations would cause deviations from perfect elliptical motion. He makes a bold prediction that this comet would return again around 758. The confidence in this prediction stems not only from the mathematical consistency of the orbital parameters, but also from Halley's understanding of planetary perturbations, a factor often overlooked by his predecessors. He implicitly acknowledges the uncertainty inherent in his calculations, particularly concerning the long-term cumulative effects of planetary perturbations, but maintains that the overall pattern of recurrence is undeniable. Section 5 Discussion of orbital variations and planetary perturbations. Here, Halley delves deeper into the complexities of planetary perturbations on cometary orbits. He recognizes that the gravitational forces exerted by Jupiter and Saturn, the most massive planets in the solar system, would significantly alter a comet's trajectory over long periods. He describes, in qualitative terms, how these perturbations could affect a comet's orbital period, inclination, and eccentricity. Halley explains that while a detailed quantitative analysis of these perturbations was beyond the computational capabilities of his time, he could estimate their approximate magnitudes based on the comet's proximity to these planets during different parts of its orbit. He underscores the inherent difficulty in predicting the precise timing of future perihelion passages due to the cumulative and often unpredictable effects of these perturbations. Halley expresses a desire for future astronomers with more advanced mathematical tools to undertake a more comprehensive analysis of these perturbing forces. This section, while acknowledging the limitations of his current analysis, highlights Halley's deep understanding of the complexities of celestial mechanics. Section 6 Classification of comets and hypotheses regarding their origin. Halley then proposes a preliminary classification scheme for comets, distinguishing between short-period comets, like the one he predicted, and long-period comets with highly eccentric orbits. He hypothesizes that short-period comets originated from the outer reaches of the solar system, perhaps captured by the gravitational pull of the giant planets. Conversely, he suggests that long-period comets may originate from interstellar space. Halley cautiously acknowledges that these are speculative hypotheses, based on limited observational data and theoretical considerations. He recognizes the need for further observations and more sophisticated models of cometary dynamics to refine these classifications and gain a better understanding of cometary origins. He understands the limitations of extrapolating from the few known comets to the entire population, and wisely avoids definitive statements regarding the origin of all comets. This section showcases Halley's willingness to speculate and formulate hypotheses, while remaining grounded in empirical observations and acknowledging the uncertainties inherent in his assumptions. Section 7 The possibility of cometary impacts and global catastrophes. In a section that resonates with modern concerns about asteroid impacts, Halley contemplates the possibility of comets colliding with planets, including Earth. He suggests that close encounters with comets could cause significant disruptions to Earth's climate and even trigger global catastrophes. He notes that the historical record contains accounts of unexplained floods and celestial phenomena that could potentially be attributed to cometary impacts. Halley frames these discussions as speculative possibilities rather than certainties. He emphasizes that the probability of such collisions is extremely low, but that the potential consequences are so severe that they warrant serious consideration. He acknowledges the lack of direct evidence linking past events to cometary impacts, but argues that the potential for future collisions should not be dismissed. The inclusion of this section, however speculative, demonstrates Halley's forward-thinking approach and his awareness of the potential for celestial events to impact human affairs. It demonstrates an early recognition of the interconnectedness of the cosmos and our own planet. Section 8 Halley's plea for continued astronomical observation. Throughout the synopsis, Halley consistently emphasizes the importance of continued astronomical observation. He argues that only through sustained and systematic observations can astronomers refine their understanding of cometary orbits, improve their ability to predict future appearances, and gain insights into the nature and origin of these celestial objects. He urges fellow astronomers to dedicate themselves to meticulous data collection, using the best available instruments and techniques. Halley underscores the need for standardized observational protocols to ensure the accuracy and reliability of data. He implores future generations of astronomers to build upon the foundations laid by his predecessors and himself, continuing a quest for knowledge about the cosmos. This section reveals Halley's deep commitment to the scientific method and his belief in the power of observation to unlock the secrets of the universe. Section 9 Considerations on the physical nature of comets. Halley, venturing beyond purely orbital mechanics, speculates on the physical nature of comets. He proposes that comets might consist of a solid nucleus surrounded by a diffuse atmosphere, reflecting sunlight to produce their characteristic appearance. He draws comparisons between the behavior of cometary tails and the aurora borealis, suggesting a possible connection between these phenomena. He acknowledges the limitations of his knowledge regarding the composition and internal structure of comets. Halley suggests a cometary nuclei may contain volatile substances and vaporize as they approach the Sun, creating the observed cometary tails. He recognizes the need for more detailed spectroscopic observations to determine the chemical composition of comets. This section demonstrates how Halley attempted to integrate observed phenomena with theoretical considerations. Even when faced with limited observational data, he recognized the limitations of a purely kinematic approach and sought to understand the underlying physics of cometary behavior. Section 10 Reception and Validation of Halley's Comet Prediction. The section devoted to the reception of Halley's prediction and its subsequent validation warrants careful attention. The anticipated return of the comet in 1758, decades after Halley's death, became a crucial test of Newtonian physics and Halley's mathematical prowess. When the comet finally appeared, albeit with a slight delay due to the more accurate calculations of Alexis Clairaut, J.M. Lalande, and Nicole Riani-Lepaute refining the perturbation estimates, it cemented Halley's legacy and vindicated his approach. The initial delay, far from discrediting Halley, underscored the intricacies of celestial mechanics and the importance of accounting for planetary perturbations. The confirmation of Halley's prediction significantly bolstered the credibility of Newtonian gravitation and solidified its place as the dominant paradigm in astronomy. It also demonstrated the power of mathematical modelling to predict future celestial events based on past observations. Section 11 Subsequent Observations and Refinements of Halley's Comet Orbit. Following the successful return of Halley's Comet in 1758, subsequent apparitions have been meticulously documented, leading to further refinements of its orbital parameters. Each return has provided valuable data for testing and improving models of cometary motion and planetary perturbations. Modern observations, using advanced telescopes and space-based observatories, have provided unprecedented detail regarding the physical characteristics of Halley's Comet, including the composition of its nucleus and the dynamics of its coma and tail. These observations have confirmed the presence of volatile substances, such as water ice and carbon dioxide, in the comet's nucleus, supporting Halley's earlier speculations. Furthermore, Studies of the comet's dust and gas emissions have provided insights into the formation and evolution of cometary nuclei. The long-term monitoring of Halley's comet has been invaluable in advancing our understanding of cometary physics and the dynamics of the solar system. Section 12: Halley's impact on cometary astronomy and celestial mechanics. Halley's Synopsis, Astronomia, Cometicae profoundly impacted cometary astronomy and celestial mechanics by demonstrating the periodicity of at least one comet. Halley transformed our understanding of these celestial objects from unpredictable portents to predictable members of the solar system. His application of Newtonian gravitation to cometary orbits provided a powerful framework for analyzing cometary motion and predicting future appearances. The success of Halley's prediction inspired future generations of astronomers to search for and characterize other periodic comets, leading to the discovery of numerous short-period comets. His work also stimulated further research into the effects of planetary perturbations on cometary orbits, leading to more accurate models of cometary motion. Halley's emphasis on systematic observation and data collection has become a cornerstone of astronomical research. His Synopsis serves as a testament to the power of observation, mathematical analysis, and theoretical reasoning in unraveling the mysteries of the cosmos. In conclusion, Edmund Halley's Synopsis Astronomia Cometicae represents a monumental achievement in the history of astronomy. Through meticulous observation, rigorous mathematical analysis, and insightful theoretical reasoning, Halley not only identified the periodicity of a specific comet but also laid the foundation for a new understanding of comets as integral members of the solar system, governed by the same physical laws as planets. While certain aspects of his analysis were limited by the computational capabilities of his time, most notably the full quantitative treatment of planetary perturbations, the core claims of the Synopsis have stood the test of time, validated by subsequent observations and refined by modern astronomical techniques. Halley's contribution transcends the specific discovery of a periodic comet. It embodies the spirit of scientific inquiry, demonstrating the power of empirical evidence, mathematical modelling, and theoretical speculation in unraveling the mysteries of the universe. The enduring significance of the Synopsis Astronomia Cometicae lies not only in its specific findings, but in its profound impact on the development of cometary astronomy and celestial mechanics, forever altering our perception of these celestial wanderers. The work invites continued reflection for its pivotal bridging of observation, calculation, and novel theoretical assertion concerning a previously enigmatic component of our solar system.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.